Hi everybody. In this video I'm going to solve an example problem involving mechanical equilibrium. Before we get started, I want to briefly review what mechanical equilibrium is. For a rigid object in mechanical equilibrium, the translational acceleration of the center of mass is equal to 0. And also, the angular acceleration is equal to 0. The absence of any translational acceleration from the center of mass entails that the sum of the forces acting on the object will be equal to 0. The absence of any angular acceleration, meanwhile, entails that the sum of the torques acting on the object, calculated about any axis, will also be equal to 0. So for a rigid object in mechanical equilibrium, this will be the starting point for our analysis. All right, so let's look at our particular problem. Imagine we have a beam of uniform density, length capital L, a total mass of capital M. Imagine that beam is being held horizontally and motionless in this configuration. We have an axle here located L/6 from the left end. This cable, which is attached to the right end, makes a 30-degree angle with the beam and also with the horizontal direction. So here's what we're asked to calculate. We're asked to calculate the tension in this cable and the horizontal and vertical components of the support force that the axle exerts to this beam in order to keep this beam horizontal and motionless in this configuration. We've located the center of mass of this beam at the middle of the beam. That's appropriate for a beam of uniform density, and assuming that this thickness here is uniform all along. Also, we're going to ignore any thickness this way so that we have a problem whose forces are completely in a single plane. And I'll say a few remarks about that at the end. All right, so given this, we want to apply this force condition and this torque condition to analyze the situation, to find the tension in the cable and the components of the support forces that this axle exerts on the beam. So in order to do that, we need to draw a free body diagram, which I'll put right here, and we'll also add a coordinate system. So here we go. All right, let's put our forces on this free body diagram, starting with the gravitational force. For an object in a uniform gravitational field, we can treat the gravitational force as acting entirely at the center of mass. So we can put that in here. The gravitational force will have magnitude capital M times G, and it's going to point directly downward. Now, in actuality, the gravitational force acts at every single point along the beam because there's mass everywhere. But for the purpose of calculation, for an object in a uniform gravitational field, we can treat the gravitational force as if it's entirely acting at the center of mass. All right, let's move on to the tension force exerted by the cable. That's attached to the right end, so that's where the tension force is being applied by the cable, and it's up and to your left, 30 degrees above the horizontal. So I'll put that in there, T. While I'm at it, I'll put in the horizontal and vertical components of that. Here's a 30-degree angle right here. All right, looking at that 30-degree angle, we can put this over here and imagine this as being a right triangle. Here's the side adjacent to the 30-degree angle where the hypotenuse is T. Adjacent side goes with cosine, so this has an amount T cosine 30 degrees. Meanwhile, this is really opposite the 30-degree angle, so this one has an amount T sine of 30 degrees. All right, great. So much for the tension force. Let's now consider the vertical and horizontal components of the support force that the axle exerts on the beam. First, let's look at the vertical component. So let's imagine we didn't even have an axle here at all. And this end would be just free to flop down. All right, so the axle is clearly keeping this end from flopping down. So the axle must be exerting an upward support force on the beam. So let's put that in there. Call that F sub V. I'm using F sub V to represent a positive number and the arrow to represent the direction of that. Just as I'm here, M times G, that's a positive number. The arrow is representing the fact that this force is in the negative direction. In the downward direction. We don't have positive and negative until we actually talk about our coordinate system, which I'll talk about in a moment. All right, now let's look at the horizontal component of the support force that the axle exerts on the beam. That could be to the left or to the right. We can do better than guess, however. Since this object has no linear, or for that matter, angular acceleration, zero linear acceleration means that the sum of the force components in each whatever component direction we take are equal to 0. So there can't be any net horizontal force component. Well, looking at the diagram as it is, there's an unbalanced leftward force component. So if this is all there is, then the support force here must be to the right in order to give us a net force horizontally that comes out to be 0. All right. Now, again, F sub h is representing a positive number. The arrow is representing the direction. If I've guessed the direction wrongly, but otherwise do the calculation correctly, this would come out negative. It won't because we've done it correctly. All right, let's talk about our coordinate system, which I've already chosen. I've chosen the positive x direction to be to your right, the positive y direction to be up. Once we've chosen x and y, that also entails a choice of z, because they've got to be consistent with the right-hand rule. X hat cross y hat gives me z hat. So the positive z direction is out towards you. Consequently, the negative z direction is in towards me. Okay. So now let's take this and apply our force condition and our torque condition. Let's do forces first because they're simpler. So this is a vector equation. We have no acceleration at all, no acceleration vector. So that means the x component of the acceleration vector is 0, the y component of the acceleration vector is 0, the z component of the acceleration vector is 0. I can write this equation for each of my 3 x, y, z components. Now, we have no forces or force components in the z direction. So we won't have a z component equation for this. We'll only have x and y components. So let's write those out, starting with the x component. So the sum of our x force components must be 0. That's the x component of this. All right, so let's look at our free body diagram. We've got, in the x direction, f sub h to the right. We've got t cosine theta to the left. Right is positive, left is negative in this coordinate system for our chosen x direction, and we've got nothing else, so we can plug those in. F sub h plus a negative t cosine 30 degrees, and that equals 0. I can go one step further and solve this for f sub h, even though my tension is still unknown. And I can note that the cosine of 30 degrees is radical 3 over 2, so I can get that f sub h is equal to radical 3 over 2 times the tension, whatever it turns out to be. All right, so where are we at now? We have one equation and 2 unknowns. In our equations so far. Overall, we have 3 unknowns. M is given, so mg is known. But f sub v, f sub h, and t are 3 unknowns. So ultimately, we're going to need 3 equations to get this done. Well, we've got one more equation left for forces. Again, we've got no z component equation that'll give us any information because we have no z component forces. However, we can look at this in the y direction. So let's do that. All right, so looking at our forces, we've got f sub v in the positive y direction. We've got mg in the negative y direction, so plus a negative mg. And we've got a t sine 30 degrees in the positive y direction. And that is it. And all those components together equal 0. All right, again, we can take this a little bit further. We have now all three of our unknowns in play. We've got f sub h here, f sub v here, and t appears here and here. Overall, we've got so far our three unknowns, but we have only two equations, so we are going to need another equation. We'll get to that in just a bit. But I will take this one a little bit further. We can solve it for f sub v. So I can add mg to both sides. I can subtract t sine of 30 from both sides. So I'll have f sub v equals capital M times g minus t sine of 30 degrees. Sine of 30 degrees is a half, so I'm going to have mg minus 1/2 times t. And that's as far as I can go for now. So, as we stand, three unknowns, but only two equations so far. All right, so let's now move over to our torque expression. The sum of the torques is equal to 0. This is a vector equation. Torque is a vector. So if the sum of the torque vectors are equal to 0, that means the sum of the torque components in the x direction are 0, the sum of the torque components in the y direction are 0, and the sum of the torque components in the z direction are 0. Now, we're not going to use all three of those equations. It turns out from mechanical equilibrium problems in which all the forces are confined to a plane, as is in the case here, the only axes that are going to give you any information that are useful beyond what you have from the force equations are going to be perpendicular to the plane in which the forces are. For us, that's going to be an axis along the z direction. All right, so the x and y components of this aren't going to give us anything. Only the z component will for the way we've set our thing up. So let's do that. So let's plug that in. Sum of the torques calculated about the z-axis must be equal to 0. That's the z component of this equation. Now, we've got this any axis. I'm free to choose any z-axis I want as long as it's perpendicular to the xy plane and has the correct positive direction out toward you. So I could choose my z-axis here. 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 Doesn't have to be on the object. What I want to do is choose the z-axis to be located somewhere that it'll temporarily take as many unknowns as possible out of play. While overall, I'm going to have three equations, three unknowns. It'd be nice if one of those equations has as few unknowns as possible, preferably only one. All right, so what I'm going to do is I'm going to choose my z-axis to be right here, coincident with the axle. I'm going to note that choice right here so that we are clear about our choice of the z-axis. Now, I need to be careful. Axle sounds a lot like axis. By axle, I mean this actual axle here, this actual location. By z-axis, that could have been anywhere. The z-axis doesn't have to coincide with the axle. I'm choosing it to coincide with the axle. Once I've chosen a z-axis for this equation, I have to use it for all my torque calculations. In the single equation, I can't go mixing and matching axes. All right, so I'm choosing my z-axis to be right through the axle out toward you. Okay, with that, we can calculate the torques produced by each of these forces or force components on our diagram. With my choice, a couple of them will turn out to be 0, and we'll see that in just a moment. But for now, I'm just going to write all the possibilities out right here for each of the possible forces or force components. I'm going to write that out right here. All right, let me explain my notation. The z subscript means these are torque components. So when you have torque components, the components themselves could be positive or negative. So each of these symbols could be hiding a negative sign or could be positive. All right, so that's why I've had this plus this plus this plus this. When I work out the signs of some of those components in the context of our particularly chosen z-axis, some of these might come out to be positive, some of them might come out to be negative, and some of them might come out to be 0. In fact, 2 of them will. All right. So now let's go about actually calculating these z components of the torques. Oh, and these other symbols, I'm just labeling the force that's responsible for the torque that we're trying to calculate. And I've created one of these for each of our forces or force components. Okay, so let's start with F sub v and F sub h. And first, we look. Here's our expression for torque. Torque is a vector. Working the magnitude out of the torque, we take the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between these two vectors. So theta in this expression represents the angle between the direction of the r vector and the direction of the force that's producing the torque. And r is a vector that points from the axis to the location where the force is being applied. Okay, so the first thing to notice is if your r, or r perpendicular, or r here, if any of those things are 0, it doesn't matter what your force is, that force won't produce a torque. And that's the case right here. Here's our axis. F sub v is being applied right at that axis, and so is F sub h. So neither of those forces produce a torque. So I can just cross those out. 0 and 0. I want to emphasize something. I'm not saying that the forces are 0. Those forces are not 0. What I'm saying is the torque produced by F sub v is 0, and the torque produced by F sub h are 0, or rather the z-axis torques are 0. All right, so these forces are not 0, but they produce no torque about this z-axis. All right, let's move to considering the torque produced by the gravitational force. First, let's look at its direction. All right, so to get the direction of the torque produced by this gravitational force about the z-axis, I need to work out this direction of this cross product. All right, so I need to work out the direction of r cross f. R points from the axis to the location of where the force is being applied, so r is this way. F, that's the force we're talking about producing the particular torque we're interested in. That's the gravitational force. That's downward. So I need to take a cross product of a vector that's this way and a vector that's this way. All right, so I take my right hand, stick my fingers in the direction of r, curl them into the direction of f, so from the first vector to the second vector in the cross product. My thumb points in the direction of the cross product and hence in the direction of the torque produced by this force. That torque is toward me. That's in the negative z direction. Great. So this z component torque produced by the gravitational force is in the negative z direction. I'm just going to put a minus sign there for that. Now let's work out the magnitude. I can use any of these expressions. I'll start with this one. So I need this amount, r. Now let's be careful. This is L over 6. And what I need is the distance from here to here. Well, this is halfway from this end, halfway from this end. So we could imagine this, we call it 3/6 L from this end. Right? If this is L, this will be 3/6 L. 3/6 L minus 1/6 L will give me 2/6 L for this distance right here. All right, so that's my R, 2/6 L. Let's put that right here. Now I need my F. That's the mg. And then I need this sine theta. Theta is the angle between r, so between this direction and this direction. Let's put those together. This direction and this direction, there's a 90-degree angle between them. So I need the sine of 90 degrees, and that's 1. But I'll write it in there just so we've got it. Sine of 90 degrees, that's equal to 1. Okay, great. We could have also just used this expression right here, where the r is the 2/6 L and the F perpendicular is mg, because it's entirely perpendicular. This is entirely perpendicular to that. All right, let's move to the torque produced by the tension force. First, let's work out its direction. So my r vector points from the axis to the location of the application of the force. So my r vector is this way. The force, that's the tension that's produced. If we're trying to calculate the torque produced by tension, then tension is the force that would go in here. So the tension force, I've got the amount here, but it's a vector in this direction. So I need to take the cross product of r, which is this way, with the tension, which is this way. So I need a cross product of this direction and this direction. I put those directions together, stick my thumb in the direction of the first vector, curl it into the direction of the second vector. My thumb points out toward u. All right, so the torque produced by the tension is out toward u. That's in the positive z direction. So I'm going to write plus, before I put in the amount, the magnitude of that torque. And now I can work out the magnitude. The magnitude I'll work out from this. I've got r. Well, now, I'm not going to write this in here, but if this whole thing is L, but this is 1/6 L, then from here to here, from this axle, from the z-axis, which I've chosen to be coincident with the axle, to this end here will be 5/6 L. So my r is going to be 5/6 L. Let's put that in. And then I need the magnitude of the force that's exerting that torque. That's T, the tension. And then I need the sine of the angle between the r vector and the tension vector. So I need the angle between this direction and that direction. Well, a whole line is 180 degrees, so this will be 150 degrees. Now, any two angles that add up to 180 degrees will have the same sine. So the sine of this 150 degree angle is the same as the sine of this 30 degree angle here. In other words, this angle and this angle have the same sine. So instead of the sine of 150 degrees, I could put in the sine of 30 degrees. And I can just squeeze this in. That takes care of this. All I'm left with here is the 0. All right. I could have done this a different way. We could note that this tension force has two components. I've got this component, which will produce no torque, because the line of action of this force component passes right through our chosen z-axis. All right, so this will produce no torque. Only this part will produce a torque. All right, and this amount is T sine 30. So using this, F perpendicular, this is F perpendicular. Only this part will produce a torque. So I could take this, 5/6 L, times this, T sine 30, same thing that I wrote here. Both these things give the same thing. All right, great. So let's finish this up. We can solve for the tension T. Let's divide both sides by L over 6. So divide here by L over 6, divide here by L over 6, divide 0 by L over 6. That's going to give us on the left-hand side minus 2 times capital M times G times the sine of 90 degrees, which is 1. Plus, again, we've divided by L over 6, so we've got 5 times T times the sine of 30 degrees, which is 1/2, and that equals 0. Let's add 2mg to both sides. So we'll have 2 times m times g on the right-hand side. On the left-hand side, we've got 5 over 2 times t. Now we can solve for t by multiplying both sides by 2, dividing both sides by 5, so that we'll get the tension is equal to 4 over 5 times capital M times G. So let's box that. All right, so we've solved for the tension. Remember, the mass was given. The mass was a known, so now we've solved for the tension. With our judicious choice of z-axis coinciding with the axle, we took some of our unknowns out of play. We ended up with an equation that had only a single unknown, and we've solved for that. So while overall we have 3 equations, 3 unknowns, our last equation had only a single unknown, and we were able to use that. Now I can take this result for the tension, plug it in here and plug it in here to get the F sub V and F sub H respectively. Let's do that right now. So plugging in for the tension, this tension here is 4/5 times capital M times G. 1/2 times 4/5 mg will give us 2/5 mg. mg minus 2/5 mg will give us 3/5 mg. So F sub V will equal 3/5 mg, and another domino falls. All right, so now we've got T, we've got F sub V. Let's get F sub H. We can do the same thing here. Let's plug in. So equals radical 3/2 times the tension, which is 4/5 mg. I'm running out of space, so I will put the answer right here. F sub H is equal to radical 3/2 times the tension, but that's the tension. 4 divided by 2 is 2. So what I'm going to have is 2 times radical 3/5 times capital M times G. And just to remind ourselves, all that's equal to F sub H. And I'll box that up right here. All right, we've done it. We've got F sub H. That's the horizontal component of the support force that the axle provides to the beam. We've got F sub V, the vertical component of the support force that the axle exerts on the beam. And we've got the tension. Let's take a look at these results. We should check that all our results have the proper units. Now, we don't have any numbers, but we can still check units. Tension. Well, we've got a pure number times a mass times G. Mass has units of mass, G has units of acceleration. Units of mass times units of acceleration give us units of force. So this has units of force. This is also some number times M times G, so this has units of force, and this has units of force as well. So the units check out. Before I sign off, I have 2 final comments. The first comment relates to all our forces being in a single plane. That turned out to be the case because we ignored the thickness of this beam. Now, even in situations where your beam has thickness, you could still have a situation where all your forces are in a single plane. So imagine I've got this beam, it's got thickness. Now, if I've got my end support like this, and then the tension cable, the cable comes from here to the middle right here, we're not going to have any significant effects involving this or this. Now, of course, the whole thing's supposed to be in mechanical equilibrium, so we can't have any angular acceleration this way or this way. But what I'm saying is there may not have to be anything interesting to prevent angular acceleration this way or this way. However, imagine this beam with some non-negligible thickness is supported over here. And imagine that the support cable comes from here and comes down over to here. Now we've got a lot of interesting things going on. This tension has a component this way, and this way, and this way. Would have it in the, something along in the negative z direction on this coordinate system. All right, so in situations like that, you can have some interesting things going on this way or this way. Again, assuming the thing is in mechanical equilibrium, there will be no angular acceleration this way or this way, but the considerations necessary to prevent angular acceleration this way or this way might be interesting and complicated. And if we then pretend that this real object actually has no thickness in a situation like that, we're going to be ignoring those types of considerations. Again, for an introductory course, that's appropriate. I just wanted to point out that in the real world, there can be some things that are more complicated, and often in the real world, you won't have forces that are confined to a single plane. All right, so that's my first comment. My second and final comment relates to what I said earlier about our ability to choose our z-axis. We chose it to be here, but I could have chosen it somewhere else. I've got lots of choice as long as I choose it to be perpendicular to the xy plane. All right, so to illustrate that, I'm actually going to choose it somewhere else. I'm going to choose our z-axis to be right here. I'm going to have it come right through this endpoint right here out toward you. All right, just to do that, I'm going to label that point. I'm going to label this point A, capital A. All right, so now I'm going to choose my z-axis to be coming through this point labeled A. In order to do our z-axis torque calculation about this point, I need to create some more board space, so I'm going to erase this. So before I do that, you should probably write it down. So here we go. I'm going to erase this. Boom. All right. I'm going to rewrite this. Sum of the torques about the z-axis equal to 0. But I'm going to use that. I'm going to call that my z-axis. I'm going to call that point A. What I mean is I'm taking my z-axis to be coming out in the positive z direction through point A instead of my original z-axis. So I'm going to calculate all my torques with reference to this axis, not this one. Well, the first thing to note is that the tension exerts no torque about a z-axis through point A because the tension passes right through point A. Likewise, F sub h exerts no torque about point A, about a z-axis through point A, because the line of action of F sub h passes right through point A. The only forces or force components that exert torques about point A are F sub v and mg. All right, so let's just continue with this equation. The sum of the torques about the z-axis chosen through point A will be equal to 0. Let's put those in. The torque produced by the tension is 0, so I'm not even going to bother to put it in. The torque produced about this point by F sub h is 0, so I'm not going to bother to put it in. I'm going to have a torque produced by mg. Let's work out the magnitude and then the sign. I've got this amount. That's going to be L over 2. And this amount of force, mg. So I'm going to have L over 2 times mg. Now let's consider whether that torque component is positive or negative. Remember, I've got my axis chosen, my z direction is out, but I need to take r cross f. My r is from here to here. My f is this way. I need to use my right hand. R cross f, so this thing cross this thing, r cross f, that's going to be out towards you. That's in the positive z direction, so I've got positive. Meanwhile, I've got the torque produced by F sub v. Let me work out the sign of that first. Here's my R from there to there. Here's my F this way. So we got R cross F. R cross F gives me a torque in toward me in the negative Z direction. So I'm going to have minus. Now, this is entirely perpendicular to this, so I'm going to have this length, which is 5/6 L, times this amount of force. That's my F perpendicular. That's F sub V. And there I have it. I want to note that the angle between this and this was 90 degrees, so I had a sine of 90 degrees here, which is 1. Here, I've got a 90 degree angle between this and this, so I've got sine of 90 degrees. That's 1 as well. All right, so I've got this minus this is equal to 0. I can solve for F sub V, and if we solve for F sub V, we're going to get 3/5 mg. Same thing as we got before. All right, so it checks out. We could have chosen our z-axis to be somewhere else. We could, in fact, still do that. We could put it other places to do other checks. So one of the great things about these types of problems is there's actually many checks that you can do. And those checks are underwritten by the fact that we have many choices for our z-axis. It even allows the possibility for other problem-solving methods. So, for example, I could have started with torques. I could have chosen this reference point. I could, a z-axis here. Then I could do it again, choosing a z-axis here. Then maybe I would have only needed one of these, and then I could use the other one as a check. All right, so while these problems are complicated and long, they're also great because they allow you to check your work. All right, that's all I've got today. This is a long video, but I hope you find this helpful. Thanks for watching, and I'll see you next time.